Thank you, and good morning, everyone. Elixir, a programming language that runs on top of the Erlang virtual machine. The goal of this talk is not to, teach you Elixir in particular. The title of the talk is actually Idioms for Building Fault-Tolerant and Distributed Applications, and that's a big part of what I want to explore in this talk. Exactly, if you're going to write systems, if you're going to write software in Erlang and Elixir, what are the different words that you need to learn? What is the way you need to think about software when you come to this platform? And this talk is going to be divided in three parts. So the first one is a little bit of history, background, why a new programming language, okay? The second one is the important part, is when we are talking about the idioms and the new vocabulary that we learn when we move to this ecosystem. And the third one is a little bit more specific about Elixir and what Elixir in particular brings to the fold. So let's get started. So to me, this journey started about almost 10 years ago. So I was used to programming Ruby, and there is a web framework called Ruby on Rails that I was used to be part of the team. And about 2008, they released the new version, and one of the big things in this new version is that Rails is thread safe, okay? And what was happening there is this story that we are hearing all the time now, that concurrency is becoming more and more important. So there was some pressure from the community to be able to get your application, put it on a server in production, and for that application to be able to use all cores. And then the Rails team decided to work on this feature. And today, and when I look back at it, right, thread safe is a very funny word. Because, so why thread safety? So in Ruby, the way you get concurrency is using threads. And safety means that you're going to get your application, run it with threads, and that's not going to blow up. And the reason why thread safety is a very funny word for me today is because it's like the lowest guarantee you can give in software, right? That's not going to blow up. Is it going to be fast? Eh. Is it going to be maintainable? Right? No, the only guarantee I'm going to give to you is that things are not going to fail. And this is actually turned to be true because later when I joined the project, we would have bug reports from, well, when I actually put a new server in production because I'm having a spike on load, I get some concurrency errors. And those would be very, very hard to debug, to reproduce, to fix. So a couple of years later, when I was trying to fix those bugs, and it was a very frustrating, very hard process, I thought to myself, wow, if concurrency is becoming more and more important, I need to have good tools. The tools we have here right now, they are clearly not enough. And I like to say that today, right, it's even more important than before. Like last year, Apple announced the Apple Watch with 2 cores. Your wristwatch has 2 cores. Writing code that runs on a single core today is the special case, right? Everything you do in your computer, in your programming environment, should be using all cores. So, yeah, I started on this journey to see what are the other alternatives, other options we had out there. And I like to say I had 2 points of no return. 2 points where when I got there, I said, okay, this changes everything, right? Like, I cannot write software that I was writing before. And the first one is functional programming. And we could have long discussions about what is functional programming. But to me, at the time, okay, it was 2 things that called my attention. So the first one is explicit state instead of implicit state. So by having objects, right, sometimes you have objects that encapsulate the object, that encapsulate another object, and then we have the state inside. And then we would have race conditions that would be really hard to detect because we would have 2 cores, right, 2 threads trying to change the same state that is hidden inside an object, this Russian doll of objects. And then it was really hard to find those cases. And then now, by making everything explicit, the state being explicit and no longer hidden away, seeing those cases where I could have race conditions just became much clearer to me. And then this was the first thing when I thought, well, if the software I was writing was using this principle, everything would be much clearer, and I would find those issues that I'm trying to debug and trying to fix much easier. And then the second one is that even if the state is explicit, what if we transform things instead of mutating them? So Elixir, the data structures are immutable. If I have a list and I try to delete an element of the list, I get a new list. I don't mutate the previous one. right? So, we could go a lot longer talking about functional programming, but those are the two things that called my attention at the time. And that was the first point of no return. The second one was when I met Erlang, the Erlang runtime, the Erlang virtual machine. So we have a bunch of functional programming languages. I decided to play with them, use them, and got acquainted with them. And there was one that I like to say that I fell in love with, which is Erlang, which is a virtual machine, a programming language, and a runtime. Okay? And what really caught my attention about Erlang was exactly how it came to be. So Erlang is as I said, programming language runtime that was built by Ericsson, which is a telecommunication company. And when they were designing it, they have a very interesting set of use cases in mind. For example, one of the things that they wanted to do is to build telephone switches. And what a telephone switch needs to do is connect person A to talk to person B. But you want a telephone switch to handle as many connections as possible, as many people talking at the same time. So we start to get this idea of concurrency, right? You should be able to handle many connections, many people talking at the same time. Another thing that they had that in there since the beginning was exactly the idea of distribution, because you have telephone switches that are connected to telephone switches. Maybe you want to call someone that is already busy talking to someone else through another telephone switch, through another way, and then you need to exchange this information and have this kind of routing through the system. And there are a bunch of other interesting features we could talk about. So I like to talk about hot code swapping, which is the ability to upgrade the code that is running live in production without bringing the system down. Because if you're building a telephone switch, there's always someone on the phone. We cannot just say, oh, we have a new version, let's just bring all the new switches up and turn off all the switches down. You can't do that, right? The calls are going to drop. That's not an option, so we need to upgrade the code live. And we have a bunch of interesting features that was designed for this use case. And Erlang was used a lot in the telecommunication area until people started to realize that this case here that we have right now, it's very similar to the web today, right? Where you have servers and you're connected to a bunch of devices, be them browsers or Internet of Things, embedded devices, mobile phones, and you want to be able to handle as many connections at the same time. We are talking a lot about having persistent connections and have information coming and going all the time. You have internal endpoints you need to talk to, right? You have other systems that you wrote and you want to communicate with them. So once this started to become clearer, a lot of companies started to use Erlang more and more. So we have Amazon and Facebook. We have telecommunication companies still like Ericsson and Motorola, and newer companies, let's say, like which today is not as new anymore, such as Heroku. So if you ever deploy an application to Heroku, every time you access your application to Heroku, you are passing through a routing layer that is written in Erlang, right? If you ever use the Riot database, that's written in Erlang as well. And there's a case that got a lot of attention in the last, I think, 3-4 years, which is WhatsApp. So WhatsApp is a messaging application you install on your phone, and you can exchange messages with your friends. And every year there is some interesting news coming from WhatsApp. So for example, in the last year or the year before, they were handling more messages than the whole global SMS system. And it's all written in Erlang. And they would go to Erlang conferences and talk about their architecture and how everything works. So this one is a bit old for now, it's from 2012, but they were saying how they got 2 million connections on a single node. So they have one node in production and they had 2 million devices connected. And this is not a synthetic benchmark. The devices that were connected, they were sending and receiving messages. And when you look at the machine, it's a quite powerful machine at the time. It's a machine with 24 cores, 96 gigabytes of RAM, and even though with that load, 2 million clients, it was using only 40% of CPU in memory. Later, they said that they got the same machine to get to 3.5 million clients. And this is exactly what I wanted. I wanted to be able to write software that is going to run on my machine with 4 cores or 2 cores as efficiently as possible, but when I put it into production and it has 24 cores, it's going to fly as well. Okay. All right, that was a very quick story of how I decided to create Elixir. It was really, I like to say, 95% of it is exactly because of the Erlang virtual machine. Elixir would not exist if there was no Erlang virtual machine. So if you want to leverage everything that Erlang has to offer, right, what those companies were using to build those kind of systems with Erlang, we need to learn new idioms. We need to rewire how we think. We need to learn new words. And that's the second part of the talk that I want to go into now. So when we go to most mainstream programming languages that we have today, this is the code that we write. We write sequential code, right? It's just a huge chunk of sequential code. And that's why threads are so hard, right? Because we need to think how those threads, they are going to interleave the same chunk of sequential code, okay? And in Elixir and in Erlang, it's not much different. We have sequential code, except that we put it into something very, very small that we call a process. So if we're talking about idioms, we just learned a new word, processes. From now on to the rest of the talk, when I say process, I do not mean an operating system process. I mean a very cheap, very lightweight thread of execution. Did I say in the WhatsApp case they had 2 million connections? They had at least 2 million processes, at least one process per connection. Okay, so they're very cheap, very lightweight. We can create a bunch of those. And those processes, they are isolated. One cannot affect each other by default. So it means that we can get all of them running at the same time. And we're already starting to have an idea of how we get concurrency. We have those isolated processes that are all running at the same time. And whenever they need to actually work together or have a common goal or coordinate, we do that by sending messages. Okay? So we are learning a bunch of interesting things. We are now thinking about in terms of processes that are isolated and concurrent. And we are now starting to talk about message passing, which is what we use for communication. Communication, coordination between processes, it's always explicit via messages. And that's the macro view, but we can actually even zoom a little bit more, okay, and try to get more information. So let's imagine that we want to get 4 processes here. Imagine, since I was talking about web applications, and imagine that all of those processes that is running on this particular node, on this particular machine, this particular instance of the VM, they are related to a web application, okay? So, and then if it's a web application, we're going to have things like we're going to have a DB process that is responsible for, talking to the database. So if you need to do a query, the DB process is going to actually send that query to the database and give you the results back. We're going to have a web process, which is something sitting at the TCP level, waiting for requests and serving those requests. We can have a statistic process that is just getting information about the system and how the system is running. And we can have a mailer process as well. Okay, so imagine every time the user sign up, you want to send an email saying welcome. So what is interesting is that if we go back to those, most of the mainstream languages we have today, there is something very weird because we have just that huge chunk of sequential code. What can happen is that if there's something wrong while sending an email, it could actually bring the whole system down. And when you think about it, it's really, really weird, right? Why something that is sending a mail can bring the thing that is sitting on the TCP socket expecting requests? Why can it bring it down? Because we have that huge chunk of sequential code, right? And the only reason we don't see it happening in practice is because we wrap the code, right? So every time the web server is actually calling your code, it wraps it in a try-catch. Or in a begin rescue, you say catching errors, rescuing exceptions. And for us, for our Erlang developers, this is a very weird idiom, right? Because exception is a way of the software to say, hey, something went wrong. And they're just saying, all right, thank you. Just continue doing whatever it's doing, right? It's a weird idiom. What if the exception that they're getting is because a state got corrupted? Asking it to continue running is not going to magically fix that state, okay? So that's the idiom that we don't like. We like to do something different. If something goes wrong with the mailer, remember those are processes. And because those processes are isolated, if something goes wrong with the mailer, it's not going to affect the other entities in your system. So what we say is, well, if something goes wrong when we're trying to send an email, something that was unexpected happened, what we want to do is let it crash, let it fail. Because what we are going to do is that we're going to define supervisors that are going to observe the processes in your system. And then if something goes wrong, the supervisor is going to notice and start a new process in place of that one to continue doing the work of sending emails. And why this idiom is so important? I like to give the example with our computer. Sometimes we're using our computer, and then there is a twitch in the corner of the screen. Or, something happens in the operating system, and it doesn't work at all. And what you do is that you restart a machine, and the problem disappears. You continue using that machine for 3 years, 5 years, and the problem never comes back again, right? And restarting fixes it, because we go back to that initial state, the initial state that's guaranteed to work, right? If there is something that the manufacturers of our computer, they cannot mess up, they are the boot instructions. Okay, those are the ones that are being tested. Every time your application, when you start or test suite, you're going back to that initial state. So here's the same idea. If something goes wrong with a process, sure, crash away. We have a supervisor. The supervisor is going to observe that and is going to act on it. And sometimes the supervisors themselves, they have supervisors, which may have supervisors. So we end up defining this supervision tree, which at the end of the day, we package into something called an application. So if we're talking about idioms, if we're talking about vocabularies, right, we're now talking about processes, supervisors, applications, and I understand that this can be a little bit too abstract. We need more concrete examples. So I want to do a very quick pause on the presentation and show an actual live demo of a system and how we can actually see those concepts. All right, so great. So what I have here is a terminal, and I just started interactive Elixir shell. Here we type regular Elixir code. I don't have time to go into the language demo. That's not the focus for today. The only thing I want to do here, so here is a web application. So we have a web framework called Phoenix, and here is a web application that is running on top of the Phoenix web framework. So I'm going to start a tool called Observer. One thing I like to joke about is that the names in Erlang, they're also really, really good, like the supervisor supervises and the observer observes. So when you do observer start, it's going to start this beautiful, beautiful, beautiful graphical user interface here, where you can see a bunch of tabs that brings all different kinds of information about your system. So the first one is the system tab, right? It's just talking about how much memory it's using. It even gives you an idea of where the memory is being used. Oh, part of it's being allocated to processes. You can see how much the code itself is taking off memory. And it gives information how many cores you have, for how long it's running, and so on and so on. Okay? And then we can get information like load charts, because I just started this node, nobody's accessing it. We're not going to get any information here. You can see memory allocators and see where the memory is allocated, and a bunch of interesting stuff. I'm not going to go through all those panes. There are two that I really love and I want to talk about. So the first one is the process. So the process pane shows all the processes that are running your system. And how can this be useful? So imagine that you have a memory leak in your application, okay? And then what you can do to try to find this memory leak is that you can open up Observer, and you can come here and say, well, I have all processes here. Let me order those processes by memory. And then if you order by memory, then you see a process that's always growing memory. You say, huh, I guess my memory leak's there. You can double-click it, and then it's going to open up another window where you can see what that process is doing, what code it's executing, what is its state, what are the messages that it still has to process, stack trace, and so on. Okay, so we can see that we're starting to get a lot of visibility into our system when we are designing with processes. Very nice. And here's something else that we can do with this pane, and this is an actual true story. So we have this Phoenix web framework, and one of the things that they wanted to do is that they wanted to reproduce the WhatsApp use case where they got 2 million connections on a single machine. So in this case, it's going to be slightly different because they want to do that over WebSockets. So the Phoenix team, they got like 40 clients to send requests to this big production server. I think it had 128 gigabytes of RAM and 40 cores. So they got all those clients set up, and they started hammering this production server. And when they started to do that, to measure their system for keeping all the clients connected, the first time they did it, they could only get 30K connections, which is way, way lower than 2 million that they were hoping for. And how did they solve that? They opened Observer, and then they came here, and they asked her to order by message queue. So what is the message queue? Every time processes, they send the messages, those processes, they go to a message queue on the recipient process, and then the process processes those messages in order. Okay? So if there is a process that is a bottleneck that everyone is trying to talk to, its message queue is going to grow and grow and grow because it cannot keep up with everyone's requests. So it just did that, and then they came and they ordered by message queue, and they could immediately see where was the bottleneck in their system. And then they said, okay, there's the bottleneck, let's fix it. They removed the bottleneck, they did it again, I think they went to 100K, and then they did the same thing, found the next bottleneck, and then they removed that one, and they got to 2 million connections. They were able to reproduce that case. That was simply using Observer to find, which process everyone's trying to talk to, where the issue is. So this is very exciting, the process pane. And I also like a lot the applications pane. So when you run a system in Airlane or in Elixir, you actually have a bunch of applications running side by side. So this Phoenix application, you can see here on the left side, you can see all of the applications that are part of the system. So Elixir itself, we can find it here. Elixir itself is an application. And you can see that it has a very small supervision tree. So what we are seeing here on the right side is a supervision tree. There's not much interesting that is happening with Elixir in terms of processes. But if we open this application itself, which is called DevApp, so if I select it, we can see that it has a bit more interesting supervision tree here. So you can see that it has a supervisor here. You can see that it has a repository. So if you want to talk to the database, we have this repository thing. And we can see here what this repository does is that it actually has a connection pool that I'm clicking here. And you can see that this connection pool has a bunch of other processes. Because when you want to talk to a database in programming languages, what you do is that you have a pool that holds a bunch of open connections to the database. And when your application needs to do a query, you get a connection from this pool, you do the query, and then you put this connection back to the pool, right? And we can see this very clearly here. Each connection to the database, different process, we have the pool process. And because we can see it here, we can actually try to reason, for example, what is going to happen if things go wrong. Imagine that there is a bug, so I'm picking the process at the top. And you can see that some processes have names because you are able to give process names. But if we don't give a process name, it's using this term, which is, in this case, like 0, 285, 0. This is the process identifier. So you can see here that I have a process identifier that is representing a connection to the database. And I can say, well, what if something goes wrong in this process? What if there is a bug? I can double-click it, and I can say, I want to kill this process. And then what we expect to happen is that if that process is supervised, something is going to notice that that process is gone, but we said somewhere that we want a pool with 10 database connections. So something should notice that and start a new connection to the database. And if we go back there, we can see that 285 is gone. And then here at the bottom, we got a new process identifier that we just added to the end of the pool. Okay, so the supervisor acted and reacted on it. So we can even do more interesting things. What if there is a bug in the connection pool, right? What we don't want to happen is to have a bug in the connection pool, and then the connection pool process goes away, and we leave a bunch of dangling database connections. That would be a nightmare, right? Because eventually you're going to have 1,000 database connections because you are leaking connections. And we can kind of already get the intuition that this is not going to happen. I don't know if you can see with detail, but we have a bunch of blue lines connecting the pool process with the connection process. And those lines, they are linked, which means that if the pool goes down, all those linked processes, they're going to go down as well. So let's see if that's what actually happens. Let's kill the pool process. And when we do that, because the pool process itself has a supervisor, we are going to start a new pool, right? And we can see here that we got a bunch of new connections. So the old ones, they're all reclaimed, right? They were all killed as well. Their connections to the database were terminated, and we started a bunch of new ones. So, all right. That's not what I was hoping for. Beautiful. So if we're talking about applications now, right, this new world that we just got it, right, we are talking about introspection and monitoring. We see how a lot of information that we can get from our system, we can start to visualize how the code that we wrote is actually going to behave at runtime. We get visibility of the application state. Because the state exists inside those processes, you can actually go through the supervision tree, clicking those processes, and see what is the state, what it's doing, what it's running. It's easy to break into components. So imagine that you're working on that application and the tree starts to grow larger or start to grow deeper. What you can say is that, well, what if I get this branch and move it to another application? We can have a bunch of applications running side by side, right? Or what if I get the subtree and move it to another application? So we have a lot of visibility on how we can break it apart. And it gives us reasoning when things go wrong. So if you're talking about idioms, right, we learned about processes. Sorry. We learned about processes, we learned about supervisors, we learned about applications. We are talking about message passing now. And we got a lot of interesting characteristics out of it. So now we're talking about concurrency. We ditched the catching errors, catch exception idiom by something like fail fast or let it crash. If something goes wrong, sure, let it crash because a supervisor is going to notice that and is going to act on it, right? And this is extremely important because it allows us to build systems that are fault tolerant, systems that when there's an error, it's going to heal itself and go back to a working state. Because it doesn't matter which programming language you're using. It can be the most advanced type system. You're going to get errors, especially if you're talking about systems that run over the network. The database just disappeared for 5 seconds, right? So we need to have this ability for the system to heal itself and go back to a working state. The creators of Airlane, so if you talk to Joe Armstrong, he's going to say, how they were using Airlane to build systems with 9 nines of reliability, right? Exactly because of this ability to heal itself. And there's something more that is actually in the title of the talk that I haven't explored yet, which is distribution. So how do we get distribution out of all of this? So if you go back to this example where you have processes that are all running at the same time, and they are exchanging messages, the message passing is abstracted away by the runtime that it actually doesn't matter if the process, they are on the same machine or they are in different machines. As long as I have the process identifier, I'm going to be able to send a message to it. Okay? And that was one of the things that really fascinated me about Erlang back then when I was exploring it. Because we're having this race for concurrency, and all languages focusing on concurrency. But what happens when you're already using all of the 48 cores in your machine? You need to have multiple machines working together towards a common goal. We need to start thinking about distribution. And Erlang is already thinking about distribution. In Erlang, concurrency is a special case of distribution where it just happens that all processes, they are running on the same machine. All right? So that was really what fascinated me. And that's what I wanted to talk to you about when we think about idioms. So this is the way we approach thinking and writing software in Erlang and in Elixir. Cool. So that was the second part of the talk. And you got this idea that, everything I was saying there, it comes from Erlang. Nothing about it is specific to Elixir. So you may be wondering, why Elixir then? Why don't I go and use Erlang? So that's the last part of the talk, okay? I want to talk specifically about Elixir and what I believe it brings to the virtual machine and the ecosystem, okay? And every time I'm talking about Elixir, I like to talk about it under the perspective of 3 goals. The first one is compatibility, the second one is extensibility, and the third one is productivity. Compatibility is easy. It just says that everything I have said so far about Erlang, it just works the same in Elixir. A process in Erlang, it's a process in Elixir. A tuple in Erlang, a list in Erlang, they're going to be tuples and lists in Elixir. We can call Erlang from Elixir and vice versa with no performance cost. So that's the first goal of the language, compatibility. The second one is extensibility. And there are different features that we have that I believe make the language more extensible. And I want to talk about 2 of them. And before I go into the features themselves, I really like this quote from Guy Steele. He gave a talk, Growing a Language, in '98. It's one of my favorite talks. And at the end he says, now we need to go meta. We should now think of a language design as being a pattern for language designs, a tool for making more tools of the same kind. And for Elixir, we express, as I said, extensibility in different ways. So one of the ways we express that is meta-programming with Lisp-style macros. So I want to show 2 examples. I won't be able to go due to time constraints into the details of the macro system, but it's nothing new. When McCarty published the Lisp papers, he talked about MLisp and SLisp. And the idea here is very similar to MLisp in the sense that we have a language that has a very straightforward translation to AST, and then we have macros that work on this AST. Just that almost nobody talked about MLisp later, right? When we talk about Lisp, everyone's thinking about the SLisp. But in this case, we went to a language that has a straightforward translation to AST, and the macros work in this AST. And here's an example of how we are using macros in Elixir. So here's some Elixir code. It took a while for you to see some Elixir code. And here's how we write test cases in Elixir. And what I want to show in this example, there is nothing fancy happening here, right? But I want to show that one macro in this example, which is the assert macro. Depending on the programming language or the test framework that you are using, this is a no-go. You should never write assert 1 + 1 = true, because if you get an error, if that thing is not true, you're going to get a report like expected true but got false, which is not really helpful. But in Elixir, assert is a macro, and as a macro, it has the ability to look into the code, to look at the environment at compilation time. So that's why we can write this code like this in Elixir. And when there's something wrong in your tests, you're going to get reports like this one. So you're going to say, well, I actually could see that we're trying to compare two things. The thing on the left is this, the thing on the right is this, and here are the value. By the way, here is a diff between those values. And here is where it happened. If you have complex expressions when you're doing assertions with variables, we extract all the variables, and in the error report we say, and by the way, this variable that you are using your assertion has this value, and this value. So it's a simple macro that can look at the assertion and try to extract a lot of information out of it to make your life better, more joyful, right? So you don't have to chase and debug the code. We are giving you all the information to you. So this is an example of getting the language and extending it to the test domain and making that a really productive experience. Here's some other example. So if you want to talk to the database in Elixir, we have this project called Acto. And in Acto, here's how you write queries. And it's very similar. We got a lot of inspiration from Link that we have in .NET and C#. But Link is literally language integrated query. But in Elixir, because we have macros, we can express our queries this way without being integrated into the language. It's just a macro. From at the beginning is a macro that allows us to write, well, from each post in post, I want to get the posts that were published before now, that I am the author and order by the time they were created. And because that's compile time, we actually look at this and we compile it as close as possible to SQL during compilation time. So when it gets to runtime and actually need to run the query, we're not wasting CPU cycles of doing that work. So those are very small examples of how we are getting the language and extending it to some particular domain. And in this case, it's going to protect you from SQL injection attacks and everything that you expect, something that runs queries against a database to protect you from. And if you go to the community, you can see a bunch of other interesting examples as well. And that's one of the ways we make the language more extensible by having meta programming with Lisp-style macros. And the second one is by providing open ad hoc polymorphism with protocols. And before I go exactly what I mean by this, let's see why we need this. So let's go back to Airlane a little bit. So imagine that someone wrote a library called JSON, and the goal of this library is to encode serialization to JSON, to encode different data types that you have in the language to JSON. And the way you would do that in Erlang, for example, is that you would define an encode function, and we say, well, when that item is a list, okay, that's how I'm going to encode that item to list. When that item is a binary, that's how I'm going to encode that item, when the item is a list, that's how I'm going to encode that list to JSON. When the items are binary, that's how I encode that binary to JSON, and so on and so on. And then after you define those clauses, okay, you're going to define this in a module called JSON, and you're going to put the source code online, okay? And then imagine that what you did is that you got this source code and you put it online. And then someone in your team is working on a particular problem. Let's call him Bob. And Bob, he realized that for that problem, if he uses a particular data structure, it's going to make his life much, much easier. So he decides, okay, I'm going to implement this data structure. And then when he comes to and then say, well, that's great, but I need to encode this data structure to JSON so I can send that information to the client. And then what Bob says, well, but the JSON library doesn't know about my data structure, right? Because that's an internal data structure here for our company. This public JSON library doesn't know how to encode it. So what Bob does, that is going to say, well, I'm going to fork that library, and I'm going to add a new clause to that list of clauses in the same module that we just saw that knows how to handle this thing. And that's great. But there is someone else, Joe, working on some other feature where he uses a different data structure. It doesn't matter which. And then he's like, well, we also need to encode this to JSON. And then Joe says, well, I'm going to fork this JSON library. And then he adds a clause, he goes back to that code, he adds a clause at the end that says, here's how you handle my data type. And now when you need to incorporate the changes from Joe and Bob, what do? You create a third fork that is going to incorporate the changes from Joe and from Bob and maintain that. That doesn't work. It's not extensible, right? So you either need to change the JSON library to allow you to pass functions around that's going to carry that information, right? And the reason because of that is because the module JSON, right, it's closed for extension, right? After I save that file on disk, I can no longer extend it, right? The only way for me to do that is by forking it and copying that file and adding new clauses. And the issue here is that we are trying to have all this logic about encoding those different data types in a single place, in a module. But the truth is, the data type is the one that knows how to convert itself to JSON. We should not centralize it there. We should ask the data type, hey, how do I represent yourself in JSON? And in Elixir, we do that with protocols. So we define a protocol, for example, the JSON protocol that has an encode function, and then we are going to call it as we would call any Elixir code, and that's it. We define the contract. And now we just implement the protocol for each data structure that makes sense. So I can say, well, the implementation of the JSON protocol for lists is this. The implementation of the JSON protocol for bit strings is going to be this one, and so on and so on. And then when Bob, he's working on his new data structure, and then he needs to teach the JSON library how to encode that data structure, he just implements the protocol for his data structure. And that's it. It's extensible, right? I can write a JSON library now that is extensible to any data type. And that's something that, as developers, we are familiar from when you're coming from a bunch of different programming languages, right? One protocol that is very common is a protocol that's related to collections. In Elixir, it's the enumerable protocol. So, for example, you can use enum_map to traverse lists, and you can use enum_map to traverse ranges. Here's a very interesting use of another protocol. So in Airlane, if I create a dictionary with key A and value 1, if you do that in the terminal, this is what you get back. You get a bunch of gibberish. You get the internal representation of the dictionary. And most of the times, unless you are debugging or fixing the dictionary library, you're not interested in that representation, right? It's actually really hard for you to find what are the keys and the values. But in Elixir, what we do is that, well, I'm going to ask the data structure what is the best way to represent itself to a developer. So the same thing in Elixir is going to return you this and say, well, the key is A and the value is 1. And sure, if you're writing the library and you want to debug, you can disable it. But by default, that's what I'm going to show you, only the details that you care about. So that is extensibility. And the final one is productivity. And productivity is kind of hard, right? How can we say that one programming language is going to be more productive than the others? We have studies that show that in some cases we actually show that, but generally speaking, it's kind of hard to assert. So what we did for Elixir is that we're going to guarantee that developers, they're going to be productive with the tooling. So I like to say, for example, first-class documentation. Documentation in Elixir should be easy to write, should be easy to read. Very good tooling, so it comes with the test framework that we saw about, interactive Elixir. It comes with a tool called Mix that gives you a mechanism for compiling your code, testing your code, and everything. So from if you install Elixir today, you're excited about the stock and you want to play with it, it takes you literally 2 commands, right, to get to a working project. You create a new project, and then you can go into it, and you can run tests, you can compile, everything is ready, okay? So here's an example of the documentation. So as I said, should be easy to write, should be easy to read. So if you document your APIs, right, you can access it from the browser, you can access it from the terminal, you can access it from your editors, it doesn't matter. It's going to be accessible, Okay. We have a package manager. If someone has solved a problem, you do not need to solve it again. And Hex is really interesting because it started as a package manager for Elixir, and it became the package manager for the whole Erlang ecosystem. So that's really nice example of the communities interacting together. And then having a bunch of available resources around. So again, if you're excited about Elixir and you want to try it out, you can just go to the website. You can go to the Getting Started. That's going to get you started with the language. If you're more interested in books, podcasts, screencasts, pick yours. You can go to the learning section, and we have a bunch of different resources available. Okay, so those are the 3 goals that we have for the language, and I think that's where it sets Elixir apart from the other languages in the ecosystem, right? So it is focused on compatibility, this focus on extensibility, and this focus on the tooling, on the documentation that is going to make you more productive at the end of the day, right? So I want to thank everyone for listening to the presentation. I also want to thank my company, Plataformatec. We are a consultancy in Brazil. We have been working with Elixir and the ecosystem for almost 6 years, and we are really proud from where we are right now. And that's all I had to share. Thank you. So for questions, there is a microphone here, I believe. So if you want to ask a question, you can go to the microphone. I'll stay around also the whole day. So if you want to come around and ask, yeah, I would love to have a conversation.
So I have a question.
Yeah, hi.
I was wondering, so you say that compatibility is one of the goals. How easy it is to have projects that have parts written in Elixir, parts written in Erlang, or basically calling from Erlang into Elixir and from Elixir into Erlang?
Yeah, so that's a very good question. So one of the things that it doesn't happen. So let's rewind a little bit to the talk. And those idioms, everything that I was saying about, it's shared by those languages, which means that data types, processes, supervisors, really the semantics, they're all the same. So it's very common, for example, that when you start with Elixir, you don't know anything about Erlang, but you're doing Elixir for 6 months, and then you go read the Erlang docs, and you can understand everything that is there because it's the same terminology. So I think interoperability is actually because of the compatibility layer. It doesn't get really messy because the concepts, the semantics, they're really the same. And then once you get past the syntax differences, it's very easy for you to mentally map from one or the other. And even to the point that we like to say in Elixir, we don't like to wrap Erlang. So if you have a library and all that's doing is wrapping Erlang calls, they say, no, there's no reason to do that, right? It's going to be fine to interface and all this interoperability. So yeah.
So that means that these protocols, they are removed by the compiler. They're not entities in the
So the protocol, that's, yeah, very good point. So the protocols, after they are compiled, they are what we call bean modules. They are the modules for the VM, and all the information you need to do for the dispatch, it's there in the modules. So if you want to just move that to Elixir, to Erlang, and use it from there, it will be fine.
Great, thanks.
You're welcome.
So if there is no other question, let's